Welcome to AP Calculus AB and BC. In this lecture, we'll connect a function, its first derivative, and its second derivative, and ask one big question. How does each graph tell the story of the others? This matters because derivatives let you describe change with precision, from motion and speed to growth rates and curve shape. Next, we'll map out exactly what we'll cover. Here is the roadmap for how we will connect a function, its first derivative, and its second derivative. The big goal is to look at one piece of information and know what it tells you about the others. First, we will read derivative information. The sign of the first derivative tells you whether the original function is increasing or decreasing. Then we will use the second derivative to describe concavity, which means the way the graph bends. We will also watch the behavior of the first derivative, because if the slopes are increasing or decreasing, that gives the same concavity information. Next, we will connect key features. Local extrema are high or low turning points of the original function, and they often line up with zeros of the first derivative. We will also use the second derivative test, which is a quick way to classify some critical points as local maximums or local minimums. Then we will look for possible inflection points, where concavity changes. A key clue for an inflection point is a sign change in the second derivative. Another clue is an extremum of the first derivative, because that can show where slopes switch from increasing to decreasing, or the other way around. Throughout the lesson, you will practice translating among graphs, tables, and sign charts. That skill is what makes these ideas useful on AP Calculus problems, because the same story can be told in several formats. So keep asking yourself two questions. What does the derivative sign say, and what feature of the graph does it create? Next, we will refresh the core derivative vocabulary before using it. Before we connect the graphs, let's lock in the vocabulary. The first derivative and second derivative each answer a different question about how a function is changing. The first derivative, read as f prime of x, gives the instantaneous rate of change of f. That means it tells you the slope of the function at a single x value. The sign of f prime of x tells direction. If f prime is positive, f is increasing. If f prime is negative, f is decreasing. Critical points happen where f prime of x equals 0, or where f prime is undefined, as long as the original function f is actually defined there. These are the x values where a local maximum or minimum might occur. The second derivative, read as f double prime of x, is the rate of change of f prime. In other words, it tells whether the slopes of f are going up or going down. If f double prime is positive, the slopes of f are increasing. If f double prime is negative, the slopes of f are decreasing. This is the language behind concavity, concave up or concave down. Possible inflection points often occur where f double prime of x equals 0 or where f double prime is undefined. But possible is important. You still need concavity to actually change. So keep the warning in mind. Critical points require f to be defined, and inflection points require a real change in concavity. Next, we'll organize these relationships into one map. Think of this map as your guide for the rest of the lecture. It lines up the function, its first derivative, and its second derivative so you can translate information from one graph to another. Start at the top with the function, f. On this graph, we describe what f itself is doing, where it is increasing, where it is decreasing, where it is concave up, and where it is concave down. Now move from f down to f prime using slope of f. If the slopes of f are positive, then f prime is positive. If the slopes of f are negative, then f prime is negative. Where f prime is 0, the original function has a horizontal tangent. That can mark a possible extremum, meaning a possible local maximum or local minimum, but it is not automatic. Next, move from f prime down to f double prime using slope of f prime. This is the key shift. F double prime describes how f prime changes, not just how the original graph happens to look at first glance. When f double prime is positive, f prime is increasing, so f is concave up. When f double prime is negative, f prime is decreasing, so f is concave down. A sign change in f double prime can point to a possible inflection point where the concavity of f changes. Keep this map in mind, because next we will use the first derivative to predict the motion of f more carefully. Now we use the first derivative as a motion report for the original function. If f prime is positive, the function f is rising. If f prime is negative, f is falling. The sign chart organizes that idea by interval. From negative infinity to negative 1, f prime is positive, so f is increasing. From negative 1 to 2, f prime is negative, so f is decreasing. After 2, f prime is positive again, so f is increasing. The numbers negative 1 and 2 are where f prime is 0, so on the graph of f, they are horizontal tangent candidates. Candidate means possible, not guaranteed. Here is the key test for extrema, which means local maximums and local minimums. If f prime changes from positive to negative, f has a local maximum. If f prime changes from negative to positive, f has a local minimum. Be careful with a common trap. A 0 of f prime alone does not prove there is an extremum. You need the sign of f prime to actually change around that point. Using the sign chart, which conclusion about local extrema of f is correct? Track the sign change at -1, then track the sign change at 2, and choose the option that matches. Correct. Phi changes from positive to negative at x equals sine 1, so f has a local maximum there. It changes from negative to positive at x equals sine 2, so f has a local minimum there. The tempting reversal mixes up the two sign change tests. So the first derivative tells us when f rises, falls, and turns around. Next, we will shift from motion to shape by looking at what the second derivative tells us. Now we use the second derivative to describe the shape of the original function. Instead of asking where the function rises or falls, we ask whether it bends upward or bends downward. If f double prime of x is greater than 0, then f prime is increasing, and the graph of f is concave up. Concave up means the graph bends like a cup opening upward, because the slopes are getting larger as you move left to right. If f double prime of x is less than 0, then f prime is decreasing, and f is concave down. Concave down means the slopes are getting smaller as you move left to right, like a curve bending downward. Here is the AP level detail to be careful with. An inflection point requires a change in concavity. It is not enough for f double prime of c to equal 0. The graph has to switch from concave up to concave down, or from concave down to concave up. For this example, h double prime of x equals x minus 1 times x minus 4 squared. The possible places to check are x equals 1 and x equals 4, because those are where the factors can make the second derivative equal 0. The sign chart shows that h double prime is negative when x is less than 1, then positive between 1 and 4, and still positive after 4. So h is concave down first, then concave up, and then remains concave up. So the concavity changes at x equals 1, which gives an inflection point. At x equals 4, h double prime equals 0, but the sign stays positive on both sides, so x equals 4 is only a candidate, not a confirmed inflection point. Keep that distinction in mind. Zeros of the second derivative are places to investigate, but sign changes confirm inflection points. You will get to practice reading these clues next. Let's pause and check how you read information from the first and second derivatives. Focus on what the sign of each derivative tells you about the original function. Suppose the derivative of f is positive from x equals -2 to x equals 1, and negative from x equals 1 to x equals 4. Which statement correctly describes where f is increasing and decreasing? When phi x 0, the function f is increasing. When phi x 0, f is decreasing. So f is increasing on -2, 1 and decreasing on 1, 4. Choice B reverses the meaning of the signs of phi. Suppose the second derivative of f is negative from x equals -3 to x equals 0 and positive from x equals 0 to x equals 2. Which statement correctly describes the concavity of f? A negative second derivative means f is concave down, and a positive second derivative means f is concave up. Therefore, f is concave down on -3, 0 and concave up on 0, 2. Choice C is tempting because it describes increasing and decreasing, but that information comes from phi, not phi. Suppose f double prime of 2 equals 0. Can you conclude that x equals 2 is definitely an inflection point of f? No. A 0 of phi is only a candidate for an inflection point. To confirm an inflection point, the concavity of f must change at that x value. Choice A is the common misconception. Phi 2 equals sine 0 alone does not guarantee a concavity change. Use the shared vertical cursor as one x value that lines up across all three graphs. Here, the point on the first derivative graph is above the x-axis, so the first derivative is positive, which means the original function is increasing near that same x value. Now move to where the first derivative equals 0. A 0 of the first derivative is a candidate for a local extremum, meaning a possible high point or low point of the original function. In this example, the first derivative changes from positive to negative, so the original function has a local maximum there. The second derivative tells you how the original function bends. When the second derivative is positive, the original function is concave up. And when the second derivative equals 0, that x value is a possible inflection point, so watch whether the concavity changes as you drag through it. When you are looking at a graph of f prime, the shape of that graph tells you about concavity of f. The key move is to notice where f prime changes from increasing to decreasing, or from decreasing to increasing. A local maximum or local minimum on f prime means the slope of f prime changes sign there. For example, increasing before a point and decreasing after, it means the slope goes from positive to negative. Here is the bridge. The slope of f prime is f double prime. So when the slope of f prime changes sign, f double prime changes sign. That is why an extremum of f prime can signal a point of inflection on f. A point of inflection means f changes concavity, from concave up to concave down, or from concave down to concave up. But be careful. An extremum of f prime does not automatically mean an extremum of f. Local maxima and minima of f depend on whether f prime changes sign, not whether f prime itself has a high or low point. Try this concept check. The graph of f prime has a local maximum at x equals 3. It increases before 3 and decreases after 3. What does this imply about f? Correct. B. Since f changes from increasing to decreasing, f changes from positive to negative, so f changes concavity at x equals sign 3. Choice A is tempting, but extrema of f depend on the sign of phi, not on extrema of phi. The big takeaway is, extrema on f prime are clues about concavity changes on f, not about high or low points on f. Next, we will use the same ideas with values in a table. Now let's practice reading all three pieces of information at the same input. This is exactly the kind of compact table setup you might see on an AP question. In the row where x equals 2, the table tells us 3 facts. F of 2 is negative 3, f prime of 2 is 0, and f double prime of 2 is 5. We are connecting the function value, the slope, and the concavity all at the same x value. First, use x equals 2 and f of 2 equals negative 3. That gives the point on the graph of f, 2, negative 3. Next, f prime of 2 equals 0. Since the first derivative gives slope, this means the tangent line is horizontal, and x equals 2 is a critical point of f. Now look at the second derivative. F double prime of 2 equals 5, which is positive. A positive second derivative means f is concave up nearby, so the second derivative test classifies a local minimum at 2, negative 3. Say the test in one sentence. F prime of 2 equals 0 gives a critical point, and f double prime of 2 is greater than 0 tells us that point bends upward, so it is a local minimum. Be careful with this common misread. F double prime of 2 greater than 0 does not mean f is increasing. It means the slopes of f are increasing, which is the idea of concave up. So the table gives us the point, the horizontal tangent, and the concavity test. Next, we will keep sharpening these distinctions so the common traps become easier to avoid. These are the traps that show up again and again when you translate between a function, its first derivative, and its second derivative. The main habit is this. Do not classify a point from one isolated fact unless the needed change is actually there. A 0 of the first derivative means the tangent to f is horizontal at that x value. But that does not automatically mean f has a local maximum or local minimum there. To justify an extremum, you need evidence, such as a sign change in f prime. If f prime changes from positive to negative, f has a local maximum. If it changes from negative to positive, f has a local minimum. The same warning applies to the second derivative. If f double prime equals 0 at c, that point is only a candidate for an inflection point. The concavity has to actually change from up to down, or from down to up. Now watch a different common mix-up. Increasing derivative describes concavity, not increasing output. If f prime is increasing, the slopes of f are getting larger, so f double prime is positive and f is concave up. So a local maximum of f prime is not a local maximum of f. It usually tells you the slopes of f stop increasing and start decreasing, which makes that x value an inflection candidate for f. Try this check. If f prime has a local maximum at x equals c, what should you first suspect about f? Choose the answer that matches the derivative to function translation. Correct. B, a local maximum of phi, means the slopes of f switch from increasing to decreasing, so f may change sign. That makes x equal sign C an inflection candidate for f, not a guaranteed maximum of f. Keep these misreads in mind as filters. Zeros need sign change evidence, and derivative behavior describes slope and concavity. Next, we will organize the translation rules into one quick reference. Use this table as your quick translation guide. The main habit is to translate one layer at a time. Derivative sign tells you motion, and derivative change tells you shape. Start with the sign of the first derivative. If f prime of x is greater than 0, f is increasing. If f prime of x is less than 0, f is decreasing. Next, watch how f prime changes sign. If f prime changes from positive to negative, f has a local maximum. If f prime changes from negative to positive, f has a local minimum. Now move to the second derivative. If f double prime of x is greater than 0, f is concave up. If f double prime of x is less than 0, f is concave down. Concavity describes the bend of the graph. When f double prime changes sign, the graph of f has a point of inflection, meaning the concavity changes there. One common AP move is reading concavity from the graph of f prime. If f prime is increasing, then f double prime is positive, so f is concave up. If f prime is decreasing, then f double prime is negative, so f is concave down. As you head into the checkpoint, keep asking, what graph or derivative am I given, and what does that translate to for f? That question will keep your reasoning organized. This final checkpoint asks you to connect f, f prime, and f double prime. Focus on what each derivative tells you: increasing or decreasing, concavity, extrema, and inflection points. On an interval, the graph of f prime is increasing. What can you conclude about the concavity of f on that interval? If phi is increasing, then ferro on that interval, so f is concave up. A tempting mistake is to connect an increasing phi directly to a local maximum of f, but local extrema of f depend on sign changes in phi, not whether phi is increasing. The derivative f prime changes from positive to negative at x equals 3. What does that tell you about f at x equals 3? When phi changes from positive to negative, f changes from increasing to decreasing, so f has a local maximum at x equals sign 3. The tempting choice x equals sign 2 reflects a common mistake. Phi equals sign 0 by itself is only a candidate for an extremum. The sign change confirms the type. The graph of f prime has a local maximum at x equals 2. Which conclusion about f is best supported? A local maximum of phi means phenges from increasing to decreasing, so phenges from positive to negative. Therefore, f has an inflection point at x equals sign 2. A tempting mistake is to say f has a local maximum there, but extrema of f come from sign changes in phi, not from extrema of phi. At x equals 1, f prime is 5 and f double prime is negative 2. Which statement correctly describes f at that input? Since f1 equals sign 5, 0, f is increasing at x equals sign 1. Since f1 equals sign 2, 0, f is concave down there. The tempting choice C gets the increasing part right, but reverses the concavity sign. To wrap up, think back to the checkpoint you just did. The goal was not to memorize 3 separate graphs, but to connect what each graph tells you about the others. From the graph of f prime, you can decide where f is increasing or decreasing. If f prime is positive, f rises. If f prime is negative, f falls, and a sign change in f prime points to a possible local maximum or local minimum. From the graph of f double prime, you can decide the concavity of f, which means the way the graph bends. Positive f double prime means concave up, negative f double prime means concave down, and a sign change in f double prime points to a possible inflection point. There is also a very useful shortcut. The shape of f prime tells concavity directly. When f prime is increasing, f double prime is positive. When f prime is decreasing, f double prime is negative. For AP calculus, the justification matters as much as the answer. Use interval signs and sign changes to support your claim, instead of pointing to one isolated value and stopping there. So your big habit is this. Ask what the derivative sign says. Ask what the second derivative sign says, and then explain it with intervals. Keep practicing that chain of reasoning, and these graph connection problems become much more manageable.